This is the third lesson on solving systems using the substitution method. In this lesson, we're going to talk about the special cases and what they look like when solving a system using the substitution method. If you recall from solving by graphing, there were three different possible cases. The first case is when the two lines intersect, giving us a point where they cross. That point where they cross is the solution. And that solution is just like the systems that we've been solving with substitution. It gives you one solution, an ordered pair, x comma y. The first of the special cases is when you end up with two parallel lines. Parallel lines have the same slope but different y-intercepts, which means that they are never going to cross. Since the lines will never meet, this type of system would have no solution. Our second special case is when you end up graphing the two lines and they are exactly the same. The equations have the same slope and the same y-intercept. In this case, every point that works for one of the equations in the system also works for the other. When you have two lines right on top of each other, you've got infinitely many solutions. So today we're going to see what that looks like when we solve using substitution. We've already done a number of problems that have one solution, so we're going to skip that first box in your notes and start with no solutions. Okay? In this system example, we have a variable x that is solved for. And that first equation in the system says that x equals 3 minus y. If this x equals 3 minus y, then the x in the second equation also equals 3 minus y at the solution point. So I'm going to rewrite that second equation, but instead of the letter x, I'm going to put a nice big set of parentheses. I'm going to write the plus y and the equals 7. And inside of those parentheses, I can put what was in the box, which was 3 minus y. Now, because I have nothing in front of the parentheses, I can just drop them. And I have 3 minus y plus y equals 7. I'm going to clean it up a little bit and combine negative y and positive y. Well, negative y plus y is going to cancel those two y's out. And we're left with 3 on the left side and 7 on the right. The variables are gone. Does 3 equal 7? No. And 3 is never going to equal 7. So that means at no point in time will there be an x and a y that will work. The variables cancel out. The numbers left are not equal to each other. So your final answer is no solution. If these two equations were graphed, they would make parallel lines. In our second special case, we're going to look at what happens when you end up with infinite solutions. When I look at my system, I do not have an equation solved for a letter, but in the first equation, y has no coefficient, meaning that the first equation would be easy to solve for a variable so that we can use substitution. So I've got 2x plus y equals 4. Draw my dividing line. I want to get y alone. So I've got to get rid of that 2x. So I'm going to subtract 2x from both sides. These cancel out, and I'm left with y equals 4 minus 2x. So the 4 minus 2x gets the box. Y equals 4 minus 2x. Since I manipulated the first equation, the second equation is where I'm going to replace y. So I'm going to rewrite that second equation. 4x plus 2y equals 8. I'm going to be replacing y, so I'm going to rewrite it one more time, but this time, instead of y, I'm going to put my parentheses, and inside of the parentheses, I'm going to put what I got for the box, which was 4 minus 2x. Now I'm ready to do step 2 of the substitution, or step 3 of the substitution method, and solve for x. So I'm going to bring down my 4x. I'm going to distribute my 2. 2 times 4 is 8. And 2 times negative 2x is negative 4x. And that all equals 8. Now I'm ready to clean it up. I've got a 4x and a negative 4x on the same side that I can combine. 4x minus 4x cancels the x terms out, and all we're left with is 8 on the left side. And on the right side, we have 8. Does 8 equal 8? Yeah, 8 always equals 8. So in this case, the variables canceled out just like in the last example, but the numbers left are equal to each other, which means that these equations end up giving the exact same line, and your final answer is infinite solutions. So now we're going to go back to that first example and review what one solution looks like. In this first example, we again do not have a letter that's already solved for. But in this first equation, we've got x and y that are easily solved for. I'm going to solve this first equation for x and do my pre-step. So I've got x plus y equals negative 1. And I'm going to get x alone. So I'm going to subtract y from both sides. And I end up with x equals negative 1 minus y. So here's my isolated variable, which means that in the second equation, I'm going to replace the letter x. Okay. Negative 1 minus y gets the box. So I'm rewriting that second equation. Instead of the letter x, I'm putting big parentheses. And I write everything else down. In the parentheses, I'm going to put what I had in the box, which was negative 1 minus y. Now I can do the distributive property. 5 times negative 1 is negative 5. 5 times negative y is negative 5y. I have my plus y from before, and my equals negative 13. Now I'm going to clean this up a little bit. I've got negative 5y plus y. So I bring that negative 5 from the front down, and negative 5 plus 1 is negative 4. Y equals negative 13. I need to get y alone. So I'm going to add 5 to both sides. Negative 4y equals negative 8. And I can divide both sides by negative 4 and end up with y equals 2. Okay? So when I solved this equation, I didn't get variables that cancel out. I was able to solve for a letter. Y equals 2. So these two lines will intersect, and where they intersect, y will equals 2. I can take that 2 and put it back in the box. X equals negative 1 minus 2. And negative 1 minus 2 is negative 3. So your solution will be negative 3 and positive 2. So what does this mean? You can get a number for x and y. So your answer is x comma y, whatever it is that you solve for, just like we've been solving our systems previously. In this specific example, again, it's negative 3, 2. On the back of your notes, you're going to solve each of the following systems. 2 of them will have infinite solutions, 2 of them will have no solutions, and 2 of them will have one solution.